Okay, so in this talk I will probably for this meeting make two blasphemous statements. So just to warn you to close your eyes. So the first one here is that, of course, we're here at the meeting talking about cosmic shear, and cosmic shear, I agree, is really one of the best probes to study dark energy and study the growth of structure and learn about possible deviation from general relativity. But we can also, rather than looking at the statistics of these matter distributions, we can look at the peaks of these matter fields. And so basically that's the study of the abundance of galaxy clusters. And I think that is still a very nice complement to cosmic shear studies. Actually, people have studied, and for the same data set, this is almost, provides almost new information. So it's not a highly correlated measurement. So I think this is a very nice complement to cosmic shear studies. And what we'll see is that actually cosmic shear and the surveys we do actually help this area of research quite well. The only problem, and this is I guess where cosmic shear to some extent is more appealing, is that if you want to study clusters of galaxies, we somehow relate what we can simulate very well, the cold dark matter distribution, to what we actually observe. Although I think if we want to do very accurate cosmic or dark energy studies, baryonic physics will become important for cosmic shear studies as well. So what we cannot do extremely well, although it's improving, is use numerical simulations to predict what we actually observe. So people have started out to observe, for instance, the X-ray properties of clusters, but they're still...
Can you put your microphone higher up? You're cutting in and out.
Okay. Like this? Better?
Cutting in and out.
Well, we could use these, but...
Get the cat down.
Could we speak back on the mic?
yeah.
Turn that down.
Okay, we'll play with the electronics. But anyway, so... Well, Richard is playing games. So this situation is proving very rapidly, but still we need good connection to the dark matter distribution. So the current situation is more or less indicated here. People do a cluster survey and outcomes cosmology, and they somehow make this miracle happen where they relate whatever they observe to the cosmology. And I think that really, this is the area where lensing can play a very important role. And that's sort of the view I have. Right now we go from observations to sort of masses to cosmology, but you would like to close this loop. Use the masses, and this would be weak lensing masses, to learn about the astrophysics, which then feeds into the simulations, which then simulate observations. And I think because this hasn't been done properly, cluster abundance studies have a rather bad reputation. But I think we can make a lot of progress here. So the real problem is getting the masses of clusters, and that's not very easy because the mass depends on all kinds of properties, dynamical state, 3D geometry, the center you've adopted, and the outer radius for measurement. And this is something which I really run into, is that theorists like to quote masses in like R200, so relative to some virial radius, or but observationally that's incredibly difficult to compare. So actually, observationally, it makes a lot more sense to use a fixed physical radius, say half a megaparsec, because that makes it a lot easier to compare people's results, for instance. Because if person A says, my M2500 is this much, and I measure an M2500, but the R25, so the radii that correspond to it don't match, I get additional scatter. So I still don't know, even for this, there are cases where for the same data people get different answers because they use slightly different relations. So I think this actually is causing a lot of confusion. But the most important part is that clusters are not simple, they're not spherical, because all these masses that people quote are spherical masses, nor are they relaxed, and especially their relaxedness, but I think all of this becomes particularly important at high redshift. And if you want to do dark energy studies with clusters, it's the high redshift end that really gives you the leverage to do dark energy. And so this is, I think, really a complicated issue. So how can we do this? So that really, I think, the key is to try to understand galaxy clusters much better. Because how are you going to measure the mass of this cluster? So this is a well-known old cluster with a very complicated mass distribution. Also in the X-rays, you see this is very complicated. So you have multiple peaks in the light distribution, mass distribution, X-ray distribution. So how do you account for this? So this is what really the question that you have in cluster abundance study. Of course, thanks to lensing, we can see dark matter, and the one thing we've learned is that it's blue. So that, yeah, you see two different clusters with blue dark matter, but I think this is the important link. So lensing provides this very important link between what we observe, and these are of course very extreme systems, very complicated merging systems, but they allow us to link the observable universe to the numerical simulation, because the numerical simulations essentially only simulate the blue parts. So lensing is great to study galaxy clusters, but there are limitations. Like, of course, if it's so good, there's always a catch. And in particular, it's the fact that we measure projected quantities. And this, again, complicates the comparison to other the baryonic traces. For instance, the X-ray properties more or less measure the virialized regions of a cluster, and it's more spherical than, say, the projected mass distribution we see here. So Nyaev-Zeldovich effect is sort of in between, as it measures the pressure along the line of sight. But still, they're slightly different. So if I have here the same cluster looking at three different projections, its X-ray properties will vary somewhat, but not as extreme as the lensing mass. So just the projected mass. So this makes it, this is a serious complication, although it's more as a source of noise. So you can account for that. So these are the limitations. So we measure the projected mass distribution. Another one, and that will be my second blasphemous statement in a moment, is that it depends on all matter along the line of sight. And another thing, but this is true for all lensing studies, it requires good knowledge of the source redshifts. And so this uncorrelated large-scale structure is an additional source of noise, and it limits the accuracy with which masses can be determined. And so here at the cosmic shear survey, I will call this cosmic noise. Because that's what it is. It's the cosmic shear, right? We look at a random patch of sky, we see excess correlations in the shapes of distant galaxies. But if I look at a cluster of galaxies, I also get that signal on top of my cluster signal. And that turns out to be complicating the interpretation of my lensing signal, although it's just a matter of noise. Like on average, the cosmic shear signal is 0. Right? That's why we measure the variance of the cosmic shear. And it's indicated here because it limits the measurement of the masses, but in particular it affects measurements of dark matter profiles most. And that's what it does, because what it does is it starts correlating scales. So when we measure the lensing signal, we measure the tangential shear around the cluster, we essentially measure the shear we bin in radial bins and assume those bins are uncorrelated. But this large-scale structure signal actually starts correlating these bins, and so here's a realization. So this is not always below the NFW line. But so here the dotted line is an NFW fit, or is the NFW that I put in. And the black line here is what you would measure with infinite signal to noise. So imagine all the sources were perfectly round, everything was perfect. You would still not recover this NFW signal. What you would recover is something that is systematically below here. But if I would have shown another realization, it would have been systematically above. So the average, when I would average over thousands of realizations, then I would recover the NFW profile I put in. But for any individual cluster, I really have to be careful in the interpretation. And that's indicated here in terms of how the signal contributes to the total uncertainty in the mass. So you see here the dotted line is the statistical error. And so basically what it shows, that the further out I go, the better my the smaller my statistical error is. But what is happening as I go further out, I'm starting to pick up more and more cosmic noise. And so the overall error indicated here is almost flat. So this is something, it's particularly important at large radii. You have to be careful, because if you don't account for this, you measure things much more accurately than you do. And it's sort of interesting, as a rule of thumb, it turns out in this case, that it's roughly, if you look at your statistical error, once you include cosmic noise, it's about double. So that, I think, is important, because a lot of people publish results of, oh, we see a deviation from the predicted concentration mass relation, but then they have errors which are a factor of 2 too small.